Thank you very much, Francesca, and thank you very much to the organizer for giving me this chance to be the first speaker of 2026. I still cannot believe that we completed the first quarter of the 21st century. So it feels, yeah, a bit weird. Okay. Anyway, so today I'm going to talk about lattices of pretorsion classes. So this is a joint work with Federico Campanini and Francesca Fedele. It was a fun project. So let's start. If I'm talking about algebras in this talk, they will be always finite dimensional over algebraically closed fields. So I'm taking some path algebra quotient by some ideals. So that's to keep in mind. Okay, and the main focus will be around torsion theory. So let's start with the definition of a torsion pair, or sometimes called torsion theory. So what you have an algebra, you have the module category, you want to break it into two pieces. So you take two full subcategories. In our case, so let's say module category of our finite dimensional algebra, and we impose two conditions. First, these two subcategories, they don't talk to each other. The second, even though they don't talk to each other, you can recover the whole module category by taking extensions. So that's the second one. So this is kind of a quick definition of the torsion theory in the module category. Okay, so the first T is called torsion class, and the second in the pair is called torsion-free class. So this notion goes back to group theory, torsion and torsion-free parts. Okay. And yeah, one quick note is that this torsion class can be thought of as a subcategory closed under images, direct sums, and extension. This is usually handy when you want to work with these torsion classes. Now, I want to move on to the notion that what if in my category there is no zero, so it's not pointed. Can I, or I take any category, can I still do torsion theory? Can I still break this category into two pieces with some properties on home and some kind of extension? So that's kind of the interesting part of this talk. So we're going to introduce a new definition, which is pretorsion theory. We are inspired by Facchini, Finocchiaro, and the following work with Grant. So they did this for any category. They tried to do torsion theory for any category, pointed or non-pointed or additive, not additive, like it's very general. But for my talk, it will be mostly, we will go back to the module categories again, but we will reinvent zero. Okay, so what we're going to do again, take two full subcategories, and we'll define that to be the set of trivial objects. So I will declare some objects to be trivial. So I'm reinventing zero here. And then we can talk about Z-trivial morphism. So a morphism will be called Z-trivial if it factors through these trivial objects that I declare to be trivial, right? Okay. And then with respect to this new zero, this set of trivial objects, we can change the condition on torsion classes as follows. So we say now, it used to be that in torsion classes, they wouldn't talk to each other, T and F, but now we are saying, okay, they can talk to each other through Z. So that's basically very vaguely saying this. And then the second one, there's a notion of Z exact sequences for this setting as well. And this setting is now called pretorsion theory. And then the first part, the first T will be called pretorsion classes, and F will be called pretorsion-free classes. So yeah, this is just what we needed. We needed this notion of Z-trivial morphisms. We can define Z-kernels, Z-co-kernels, because these definitions are quite general. We have to do this carefully, so I'm skipping these details over. And let's note that any torsion class will be a pretorsion class. So if you have a pointed category, you have 0, and then the pretorsion will be just torsion theory with respect to 0. So now what we can do, of course, as we do in torsion theory or torsion classes, we can form the poset of pretorsion classes. So we look at we have an algebra, we have the module category, we ask, let's take all the pretorsion classes. This is a poset by inclusion, as usual, as in the torsion theory. But then the question, is it a lattice? Yes. So the lattice of, the poset of pretorsion classes form a lattice, meet being the intersection, join being the smallest pretorsion class containing these two objects. So quite nice and maybe expected. Here is a small example in A2. Wait. Okay, I'm watching the time. So it's a very small example in A2, and then I just want you to keep in mind the picture of this lattice. And Federico and Francesca in an earlier work actually introduced some methods. How do I create pretorsion classes or theory from torsion classes? And it's kind of cute. You look at the lattice of torsion classes and pair the torsion part here, torsion-free part here, and this gives you a pretorsion theory. So there is some techniques which I will refer to earlier paper of Federico and Francesca. Okay, what we did, when we have a lattice, the first question, what are the joint irreducibles? So we classify them. They actually, joint irreducibles of this lattice are in bijection with the indecomposable objects in our module category. Further, of course, then we can ask, when the joint irreducible of pretorsion lattice coincide with the torsion lattice, and this happens only when we have a locally representation directed algebra, you can guess this is because we want every indecomposable to be brick. Okay. And then the next theorem we have is, we have a lattice. In the lattice of torsion classes, it's never distributive. It's only in the trivial case. We have distributivity for torsion classes, but it's not the same in lattice of pretorsion classes. We have way more distributive lattices when we consider the poset of pretorsion classes, and we need the necessary condition for this lattice to be distributive. And further, we actually explicitly say when this lattice is distributive by just looking at certain sub-Q in your Q you start with. So this is it's very local around the vertex. Here the sources can be the same, can be the different, or can start even at the same place. So this, you should be thinking, okay, this is bad if I have two things coming in. This is bad if I have three arrows going out, and if I have something with no relation. So in this form. Okay, so this is then we really, there are plenty of distributive lattices here, but we also know when our algebra, the module category, pretorsions in the module category will give rise to a distributive lattice. I'm looking at the time. Okay, so here is the lattice of pretorsion again, and if you're combinatorially minded, you may see this. It's something between weak order in the corresponding Weyl group and Brucha order. And then you can ask further question, what is happening here? And this is, for instance, an example for A3. You take any orientation here, and these are the lattices. Two of them are distributive, one of them is not. So you see it's quite, 2 out of 3 is quite a lot. We have good number of distributive lattices here, but the number of elements high is the cardinality of the Weyl group. And this was at first a very surprise to us, but then actually Rene pointed out a paper where the paper by Opperman, Wright, and Thomas, they actually classify quotient closed subcategories, and they show there's a bijection to the elements of the corresponding Weyl group. And it turns out actually the Pretorsion classes in this case are just quotient clause subcategories. So it's quite an interesting remark. Thank you.